Hello all, I am Saraswati, working as Associate Professor, Department of ECE, K.S. Rangasamy College of Technology. The course name is Control System Engineering. Today topics we are going to discuss frequency response and system analysis. So the introduction, let's see what is sinusoidal response. The response of the system for the sinusoidal input is called sinusoidal response. Next, what is sinusoidal transfer function of the system? The ratio of sinusoidal response and the sinusoidal input is called sinusoidal transfer function of the system and is denoted by T of j omega. The sinusoidal transfer function is the frequency domain representation of the system, and so it is also called frequency domain transfer function. Next, how will you find the sinusoidal transfer function? Let's see one by one. The first step, we construct the physical model of a system using basic elements parameters. And second step, determine the differential equations governing the system from the physical model of the system. Third step, taking Laplace transform of differential equations, then determine S-domain transfer function, which is the ratio of S-domain output and input. And next, finally, determine the frequency domain transfer function T of j omega by replacing S by j omega in the S domain transfer function T of S. Next, what is frequency response? The frequency domain transfer function T of j omega is a complex function of omega. Hence, it can be separated into magnitude function and phase function. Now, the magnitude function and phase function will be the real functions of omega and they are called frequency response. And what are the advantages of frequency response analysis? The first point, the absolute and relative stability of the closed loop system can be estimated from the knowledge of their open loop frequency response. And second, the practical testing of systems can be easily carried out with available sinusoidal generators and precise measurement equipment. Third, the transfer function of complicated systems can be determined experimentally by frequency response test. And fourth, the design and parameter adjustment of the open loop transfer function of a system for specified closed loop performance is carried out easily in frequency domain. And fifth, when the system is designed by use of frequency response analysis, the effects of noise disturbance and parameters are relatively easily to visualize and incorporate corrective measures. And sixth, the frequency response analysis and design can be extended to certain nonlinear control systems. So next topic, frequency domain specifications. So in this topics we discuss what are the frequency domain specifications. The performance and characteristics of the system in frequency domain are measured in terms of frequency domain specifications. So there are 6 frequency domain specifications in frequency domain. The resonant peak, resonant frequency, bandwidth, cutoff rate, gain margin, and finally phase margin. Let's see one by one. What is resonant peak? The maximum value of the magnitude of closed loop transfer function is called a resonant peak. At large, resonant peak corresponds to a large overshoot in transient response. The mathematical expression for resonant peak, MR is equal to 1 by root of 1 minus del square into 2 del. And resonance frequency, the frequency at which resonance peak occurs, it is called a resonance frequency. The mathematical expression omega r is equal to omega n root of 1 minus 2 del square. The resonance frequency is dependent on natural frequency, undamped natural frequency omega n and the damping ratio. Hence it is indicative of frequency of oscillation and the speed of response of the time response. And bandwidth, it is denoted by omega b. The bandwidth is the range of frequency for which normalized gain of the system is more than minus 3 dB. The frequency at which the gain is minus 3 dB is called a cutoff frequency. The mathematical expression for bandwidth is given by omega b is equal to omega n root of 1 minus 2 del square plus root of 2 minus 4 del square plus 4 del 4. As cutoff rate, the slope of the log magnitude curve near the cutoff frequency is called a cutoff rate. And gain margin, the gain margin is defined as the value of gain to be added to system. So in order to bring the system to the verge of instability, the gain margin is given by the reciprocal of the magnitude of open loop transfer function at phase crossover frequency. Next, what is phase crossover frequency? The frequency at which the phase of open loop transfer function is 180 degree minus 180 degree is called a phase crossover frequency. It is denoted by omega pc. The mathematical expression for gain margin kg is equal to 1 by magnitude of open loop transfer function g of j omega at phase crossover frequency omega pc. And gain margin in terms of dB, so kg in dB equal to 20 log kg equal to 20 log of 1 by magnitude of g of j omega pc. And the phase margin, the additional phase lag to be added at the gain crossover frequency in order to bring the system to the verge of instability. The definition of the phase margin is obtained by adding 180 degree to the phase angle pi of the open loop transfer function at the gain crossover frequency. Next, what is gain crossover frequency? The gain crossover frequency omega gc is the frequency at which the magnitude of the open loop transfer function is unity or in 0 dB. So the phase margin is denoted by gamma. The gamma is given by gamma is equal to 180 degree plus pi gc. The pi gc is nothing but the phase angle of open loop transfer function at gain crossover frequency. Next, the frequency response plots. The various graphical techniques available for the stability frequency analysis are Bode plot, polar plot, Nichols plot, M and N circles and Nichols chart. So now we see the Bode plot. Now what is the Bode plot? The Bode plot is the frequency response plot of the sinusoidal transfer function of the system. It is called the Bode plot. The Bode plot consists of two graphs. One is a magnitude plot, second is the phase angle plot. The magnitude plot is nothing but the magnitude of a sinusoidal transfer function versus log omega, and the phase angle plot is the phase angle of a sinusoidal transfer function of versus log omega. Next, the basic factors of g of j omega. So there are the basic factors of g of j omega. First one is constant gain k, integral factor k by j omega or k by j omega power n, derivative factor k of j omega or k into j of omega power n, first order factor in denominator 1 by 1 plus j omega t or 1 by 1 plus j omega t power m, first order factor in numerator 1 plus j omega t or 1 plus j omega t power m, and sixth quadratic factor in denominator 1 divided by 1 plus 2 del of j omega by omega n plus j omega by omega n whole square. Quadratic factor in numerator 1 plus 2 del into j omega by omega n plus j omega by omega n and whole square. So these are all the basic factor of g omega. So this basic factor is used to and plot the Bode plot. Let's see one by one. So constant gain k. So the constant gain k is represent g of open loop transfer function, g of s equal to k. Now first find the sinusoidal transfer function. The sinusoidal transfer function nothing but replace the s by j omega. So now substitute s is equal to j omega. So g of j omega equal to k, and from this find out the magnitude part and the phase angle plot. The magnitude plot is nothing but magnitude of g omega is equal to k. In terms of dB, 20 log k. The phase angle plot is pi of equal to, and here the k only the imaginary part, there is no real part, there is only real part, there is no imaginary part, therefore the phase angle is a 0 degree. So this is a Bode plot of constant gain k. When the k is varies k is equal to 1 or k is equal to greater than 1 or k is equal to less than 1. When k is equal to greater than 1, the magnitude of g omega in positive dB. When k is less than 1, the magnitude of g omega is a negative value. When k is equal to 1, the magnitude of g omega in 0 dB. And the phase angle is 0 degree for all the value of omega. So the magnitude plot is a horizontal straight line at the magnitude of 20 log k dB, and the phase angle plot is a straight line at the 0 degree. Okay, so next, integral factor. So the integral factor is written as g of s equal to k by s. Now the s, substitute s is equal to j omega. Therefore g of j omega equal to k by j omega. Next, find out the magnitude plot and the phase angle plot. The magnitude of g of j omega in TB is equal to 20 log of k omega. And the phase angle is pi is equal to minus 90 degree. So when omega equal to 0.1 and substitute omega equal to 0.1 k in the expression A. So we got A is equal to 20 dB. When omega equal to k, the magnitude of g of j omega in 0 dB. When omega equal to 10k, the magnitude of A is a minus 20 dB. So this is the Bode plot of k by j omega. Okay, so the magnitude plot is of the integral factor is a straight line with a slope of minus 20 dB per decade, and the passing through the 0 dB when omega equal to k. Okay, so this is a magnitude plot, and the phase angle is a straight line at a minus 90 degree. So it's a independent of omega value. Okay, next, when the integral factor has multiplicity of m, so then g of j omega equal to k by s power n. So now s is replaced by j omega. Therefore g of j omega equal to k by j omega power n. And find the magnitude plot and the phase angle plot. The magnitude of g of j omega in dB equal to 20 log of k by omega n, when the phase angle is pi is equal to minus 90 n degree. And the magnitude of g of j omega equal to 20 n log of k power 1 by n by omega. Now substitute various values of omega value. So the magnitude plot is a straight line with a slope of minus 20 n dB per decade and passing through the 0 dB when omega equal to k value. Okay, so when omega equal to 0.1 power k power 1 by n and the plus 20 n dB, when omega equal to k power 1 by n, so we get 0 dB. When omega equal to 10k power 1 by n, the magnitude of g of j omega is a minus 20 n dB. Okay, so this is a magnitude plot, and the phase plot is a straight line at minus 90 n degree, is independent of omega value. Thank you.